we've traveled back in time 100 years when the algorithm was one of the only teaching strategy for big vertical subtractions. So we are going to try to solve 852, take away 389. We're going to estimate first because we're modern mathematicians and we always estimate. So roughly 850, take away roughly 400, expecting roughly 450. Then we have it set up with materials because modern mathematicians and teachers use the concrete pictorial abstract approach, not just the chalkboard, which is abstract only, or the whiteboard, or the interactive, or the PowerPoint, which is also abstract only. Sometimes might have pictorial, but definitely not concrete. So we've got here 852, but set up as one of the hundreds is able to be renamed because it's made of 10 tens with a rubber band. One of the tens is able to be renamed as connectable ones blocks. So it's ready for renaming when we need it. So whenever you're setting up a vertical subtraction that might involve renaming, I'd ask the students to set that up. With most of the place value blocks just set up as normal, but with at least one of the hundreds as 10 tens and one of the tens as 10 ones. And that's all you need because you only need to rename one place value to get enough to subtract. So let's set it up vertically. 852 take away 389. Now we think in traditional mode, we start with the ones, 2 take away 9. We can't do that, well we can, but it's a negative number. So instead we're gonna break up this 10 and rename it into 10 ones. We'll check it's 10 first. So we'll actually rename it to the point where we can see 5 and 5 to trust that it's a 10. I like arranging it like a dice, like 5 and 5 on the dice to trust it. And so we can see we've got 12. If we then take away 9 and put them there as 4 and 5, so we can just check that our taken away component is something that we believe is correct at the end of the equation. We can check we've taken away the right amount. Then we're left with 3. So essentially what we did there was we took a 10, we now have 4 tens, we made it 12, and it left 3 once we took away the 9. Now we have 4 tens and we need to take away 8 tens, which we don't have unless we rename. So we go here and we rename one of the hundreds, and that's when we take it apart, that rubber band comes off. Excuse it's a little messier because I don't have 2 hands. We'll check it has 5 and 5, and it does. It has 3 and 2 and 3 and 2. So it has 10 tens, and now we need to take away 8 tens. So we'll take away these 8 tens, maybe 4 and 4 we will arrange those as to check that that's 8, and we are left with 6 tens there. And what we were really doing there was we had one of the hundreds became 10 of the tens, became 14 tens as we saw, and then we took away 8 tens, which left us with 6 tens. Now we have 700, 400s and 300s, 700s. We need to take away 300s, that's nice. It just leaves 400, so 463. And we can check that we took away the 389, 389, so that's our taken away component. Nice if you have red paper, because red invokes a takeaway or a debt or something like that. And then if you arrange this like that to see 463, or even the 200s and 200s, so it's really clear. And that is how you would model vertical subtraction with materials, so you can see what's happening in each of those stages with the place value blocks, rather than just crossing out, borrowing from the neighbour type of explanations without actually understanding what's happening to the numbers. That's why you use place value blocks in place value, but then you bring them back for subtraction. And then we check against our estimate, 450, 463. Sounds very close, it's a reasonable answer, so we might smiley face it or tick it. We know we're probably about right, or at least it's a reasonable answer. It's not an unreasonable answer that something's gone horribly wrong. We might still be wrong, but we're not gonna be horribly off the mark given our estimate. But now, let's switch it up. Let's get away from this and let's get back to modern society, away from this 100 years ago. And we do prefer our houses today. So let's use a different strategy. One strategy that I love is the pump it up strategy, or essentially transformation in technical talk, but I call it pump it up because there's a song for that. Kids remember that more. So for pump it up, you have to change both numbers by the same amount. Then the difference will be the same. The explanation is really, well, 7 take away 3. If you add 3 to both, that's the same as 10 take away 6. The answer's still 4, right? Or even if I added 100 to both, the answer's still 4. Yep. So you need to understand constant difference first, that whatever you do to one, if you do the same to the other, the difference will stay the same for subtraction. So if I add 11, I'm adding 11 to make this a pretty swan. It's an ugly duckling. 389, ugly duckling. Mother kicks it out of the nest and says, go away, please. You're not welcome here. Gives it a slap on the butt with a ruler and says, off with you. But 400 I can work with. 400 is a pretty swan. And then this becomes 863. Well, take away 400, just becomes 463. So much easier, so much less process, so much less recipe, so much more number sense and creative thinking involved in that. You've got a few other strategies. So that's called pump it up, transformation, but I like to call it pump it up because we can play the song to remember that strategy. We've also got jump the difference, jump the difference. Now for this one, you usually start at the small number, the taken away number, 389. What you're trying to do is get to the starting number, and whatever you need to jump will be the difference, because subtraction is not just take away, it's difference between. So from 389, I'm gonna get my green that jumps me, it saves me if I'm doing this jump across a gorge. I'm sort of going, ooh, okay, how do I get there? So if I add 11, and I'll make that a small jump actually, because it's just a small amount that I'm adding. If I add 11, that gets me to 400. And then I can probably, I can do this in bits, but I can probably do the whole 452 at once to get me to the 852. So add 11, 400, add the rest to get to there. This becomes the answer, the difference. So that's 463. The 11 plus the 452, whatever I had to jump to get from there to there. You can also do jump back, which is a bit more innate, because we like to think of subtraction as takeaway. It's the first way we're taught it as students. So 852 would be what you'd start from, 852. And then you might decide to, well, 389 is so ugly. I'd have to jump back 300, jump back 80, jump back 9. No, thank you. So let's just jump back the whole 400. Jump back 400. I'm gonna make that bigger, so I have more space. Jump back 400. That would be 452. But whoops, I wasn't meant to jump back 400. I was meant to jump back 389. So I need to add 11 back on, because I sort of cheated. So I add 11 back on. So that becomes 463. Same answer. So that one's called jump back. Jump back. But it also has a bit of rounding and adjusting in it, which is a strategy that goes across every operation, round and adjust. That's where my brain goes in terms of that equation. But if you can think of any other strategies, I'd love to hear of them. We'll pump it up, drop it low. It can work as well. You can always drop an equation low, but that one, it's already at 389, so it's much closer to 400 than dropping it down to a pretty number that's below 389. Rounding and adjusting, we did. You can do expanded form subtraction. Let's try that and just see its comparison to this. So that would be 800. You might break it up though, the 852 into 700 and 100, and let's break it into 40 and 12. Sort of how we set it up there, where 100 was made of 10 tens and one of the tens was made of 10 ones. And then once you've broken it up in a flexible way like that, it still makes 852. Then you can just take away the 300 from here, the 80 from here, and the 9 from here. And that then makes you 400 and 20 and 40 and 3, which becomes 463. It's just so many strategies.